Chapter 2, Section 6, Physics Talk, the Law of Conservation of Momentum. In this section, you investigated a conservation principle that is a hallmark of physics, the conservation of momentum. You found evidence of the conservation of momentum when a moving cart hit a stationary cart and they stuck together. Momentum is also conserved in all the collisions you illustrated at the end of the investigation. One of these collisions, type 2, is sometimes called an explosion. If you add up all the momenta before a collision or explosion, you know that the sum of all the momenta after the collision will be the same. That is what physicists mean by the word That is what physicists mean by the word conserve. The total momentum is conserved because its value remains the same. In the first collision of the section, a moving cart hit a stationary cart and they stuck together. The same thing happens in a traffic accident. If the momentum before a collision is 5,000 kilograms times meters per second, then the momentum after the collision must be 5,000 kilograms times meters per second. Imagine a vehicle stops at a red light. The vehicle is not moving and therefore has a momentum equal to 0. If a second vehicle that has a momentum of 5,000 kilograms times meters per second then hits the stopped vehicle, both vehicles move off with a combined 5,000 kilograms times meters per second of momentum. Total momentum stays the same, or, in other words, total momentum is conserved. You can write this as an equation and substitute values for the masses and velocities of the vehicles. Momentum before the collision equals momentum after the collision. Okay, so the mass of object 1 times the velocity of object 1 plus mass of object 2 times velocity of object 2 equals the mass of object 1 plus the mass of object 2 times the final velocity. You add the masses after the collision because they stuck together and travel with the same speed. Conservation of momentum is an experimental fact. Physicists have compared momentum before and after collisions between pairs of objects ranging from railroad cars slamming together to subatomic particles impacting one another at near the speed of light. Never have any exceptions been found to the statement the total momentum before a collision is equal to the total momentum after the collision if no external forces act on the system. This statement is known as the law of conservation of momentum. In all collisions between vehicles and trucks, between protons and protons, between planets and meteors, the momentum before the collision equals the momentum after the collision. A single cue ball hits a rack of 15 billiard balls and they all scatter. It would seem as if everything has changed. Physicists have discovered that in this collision, as in all collisions and explosions, nature does keep at least one thing from changing, the total momentum. The sum of the momentum of all the billiard balls immediately after the collision is equal to the momentum of the original cue ball. Nature conserves momentum. Irrespective of the changes you see, the total momentum undergoes no change whatsoever. The objects may move in new directions and with new speeds, but the momentum stays the same. Conservation of momentum is crucial physics for analyzing any collision between objects. Traffic accident investigators use tread marks, the positions of the automobiles, and the damage to the automobiles to understand what happened at the time of the accident. They also use the physics principle of momentum conservation to help them in their analysis. If you know the masses and velocities of two objects before a collision, you can accurately predict the velocities after the collision. Physics allows you to predict the future. Solving conservation of momentum problems is easy. Using the definition of momentum equals mass times velocity. Calculate each object's momentum before the collision. Calculate each object's momentum after the collision. The total momentum after the collision must be equal to the total momentum before the collision. Sample problem 1. A boy and a girl are riding in bumper cars at an amusement park. A 75-kilogram boy and car are moving to the east at 3 meters per second toward a 50-kilogram girl and car who are moving toward him west at 1.8 meters per second. If they catch up, stick together, and then move away together, what is their final velocity? Okay, the strategy is, let me move back up so you can see the numbers. And actually, I want to scroll up so you can see the problem too. Okay, the strategy is, this is a problem involving the law of conservation of momentum. The momentum of an isolated system before an interaction is equal to the momentum of the system after the interaction. As you are working through this problem, remember that the velocity in this expression is velocity and that it has direction. Remember, the velocity in this expression is velocity and that it has direction as well as magnitude. Make east the positive direction and then west will be negative. Okay. So you have the mass of the boy, the mass of the girl, the velocity of the boy, the velocity of the girl. So they've given you all those numbers. Now you're just plugging them in to the equation, okay? So you've got your mass of your boy, you're going to plug in there, velocity of the boy. So the mass of the boy times the velocity of the boy plus the mass of the girl times the velocity of the girl equals, all right, and then you're just going to plug that in, and then you would just calculate that. All right, let me scroll down. Sample problem 2. A steel ball with a mass of 2 kilograms is traveling at 3 meters per second west. It collides with a stationary ball that has a mass of 1 kilogram. Upon collision, the smaller ball moves to the west at 4 meters per second. What is the velocity of the larger ball? Strategy. Again, you will use the law of conservation of momentum. Before the collision, only the larger ball has momentum. After the collision, the two balls move away at different velocities. Given that before the collision, these are your values, mass of object 1, mass of object 2, you have your velocities, and basically you're just proving that you're calculating and proving that the momentum before equals the momentum after. And we can do this. This is asynchronous time right now, but during synchronous time, if you need help either one-on-one or during the whole class discussion or small group discussions or individual phone calls or individual support, Ms. McEntee and I can definitely support you with this. Okay.